All right, guys, it's time for fun with math. And today we're going to finish up this lecture on integration by partial fractions here. Before we get to the problems, though, I want to review with you guys how to divide polynomials. So the reason I want to do this is remember that partial fraction decomposition theorem, what it actually says is that every rational function can be expressed not only as partial fractions, but also as a polynomial, right? So it's a sum of a polynomial and then some partial fractions afterwards. We did not have to deal with the polynomial piece because our degrees on top were always smaller than the degree on bottom. So let's look at this one right here. And what you want to notice is that the degree on top here is 5 and the degree on bottom is 2. So now the degree is bigger on top than it is on bottom. So to do this partial fraction decomposition, we have to do one additional step. So what do we need to do? We need to divide these two polynomials here. So how do we divide polynomials? So let me just kind of review this idea with you. And I usually try to take something kind of simple, like let's do like 7 divided by 2. How do you divide 2 into 7? There's actually a couple of ways to do this. The way you may be most familiar is just do long division. So you put 7 on the inside, you put 2 on the outside. We say 2 goes into 7 3 times, and 3 times 2 is 6, and then we subtract, we get a remainder of 1. And so then we can rewrite this as being equal to, you have like the whole part, so 3, and then plus, and then we have this little remainder afterwards, so 1 divided by 2. So 7 halves is 3 plus 1 half. So every rational number can basically be expressed as a whole number with a sort of remaining fraction left over. You can do the same thing with these polynomials. So if you ask me to divide that polynomial there, I just kind of follow this as a template. So I'm going to divide. And what am I going to divide? Well, notice here, 7 went inside this sort of division here. And so here I'm going to put x to the fifth plus 3x on the inside, and I put x squared minus 1 on the outside. So I always tell you guys, this is kind of like my experience that I completely understand, and then do the more abstract division. I just use that experience, I reflect upon it, and kind of go back and forth to get the abstraction. And so now what do? Well, just like this one, 2 goes into 7 3 times. It's kind of like how many times does x squared minus 1 go into x to the fifth plus 3x? And here I'd write this as going in there x cubed times, because x cubed times x squared, when you multiply this, I get x to the fifth. And then minus, I multiply it by 1, I get x cubed. And then what I'm going to do is just subtract this off from the top. Just like here, I did 7 minus 6 and got 1. So now here, the x to the fifths are going to cancel. I have 3x minus a minus x cubed, so I'm going to get an x cubed plus 3x back when I subtract that. And then I do it again. And so now I look at this and figure how many times x squared goes into that. So x squared goes into that plus x times, because if you multiply x times this thing here, I'm going to get x cubed minus an x times 1 is an x. And now I'm going to subtract this off. And so now the x cubes are going to cancel. I get 3x minus and minus to plus x, and so that's 4x. And now I got it. And so what is this equal to? Well, I have my whole part right here. That's the polynomial part, so x cubed plus x. And then plus, I have this remainder right here of 4x, so 4x. And then I'm dividing it by this x squared minus 1. And that's how we divide polynomials using what's called long division. And so once I've divided this polynomial, now notice the degree on top is bigger than the degree on, or smaller, I'm sorry. The degree on top is smaller than the degree on bottom. And so now I can apply those partial fractions. So this is going to be equal to x cubed plus x, and then plus, and remember, x squared minus 1 is really an x minus 1 times x plus 1. And so that's going to be an a over x minus 1 plus a b over x plus 1. And there's this partial fraction decomposition. It has a polynomial part and then partial fractions right there. The sum of polynomial and partial fractions, basically. All right, so you have that one extra step that you have to do if the degree is bigger than on top than it is on bottom. So be careful about that. Let's do this example. And so here we have our example right here, A. I'm going to rewrite that here so we have lots of space. So we need the integral of x to the fifth plus 3x over x squared minus 1 dx. And I already did the long division, so normally to have to do this, right below it. But since I've already done it, I can rewrite this as the integral. We said this was x cubed plus x plus a 4x over x squared minus 1 dx. So that's what the long division gave me. And now I can factor this bottom like we just did up there. So this will be equal to the integral of x cubed plus x plus, and this is 4x over x minus 1 times x plus 1 dx. And I can apply my partial fraction decomposition to this guy right here. So I'll rewrite this as x cubed plus x plus a over x minus 1 plus b over x plus 1, and then all dx. And then what you want to realize is I can actually integrate these two things out. That's not too hard to do. There's polynomials, so I add 1 and divide. So this will be x to the fourth divided by 4 plus, and then x squared divided by 2. And I have this integral left over, a divided by x minus 1 plus b divided by, let's fix that, x minus 1. So x minus 1. And then plus b divided by x plus 1. And now I just have to figure out what a and b are. So how do you figure out a and b? So I'm going to take this thing, which is equal to that thing. So over here, I have 4x over x minus 1, or x minus 1 times x plus 1. And I set it equal to a over x minus 1 plus b over x plus 1. I'm going to clear those denominators. So just clear out the denominators. So I multiply by x minus 1 and x plus 1 on both sides. If you multiply this side by it, this stuff's going to go away, and I'm just left with 4x. If I multiply this by x minus 1 times x plus 1, the x minus 1s are going to go away, and I'm left with a times x plus 1. And then plus, if I multiply this by b divided by x plus 1, the x plus 1s are going to go away, and I'm left with an x minus 1. So I have b times x minus 1. And now I just can plug in points. So let's just plug in, I don't know, let's plug in x equal 1. If you plug in x equal 1, what does this do? So it implies that I have 4 times 1 equal to a times 1 plus 1 is 2. And then, of course, this is going to wind up being 0 when you plug in 1. And so this implies what? This implies that 4 is equal to 2a. And so this implies that a is equal to 2. So now I know my a is 2. And then to figure out my b, I'll do the same thing, but I'll plug in x equal to negative 1. So if x equals negative 1, what's going to happen? So I just plug in here. So I have 4 times negative 1 equal to, this is going to go away because when you plug in negative 1 and add 1, it's going to be 0. And over here at b times negative 1 minus 1 is negative 2. And so this is going to tell me my b is actually equal to what? Well, I have negative 4 divided by negative 2, so that's a positive 2. So a is 2 and b is 2. And so I'll come back over here now, and this is going to be equal to then x to the fourth divided by 4 plus x squared over 2, and then plus a 2 divided by x minus 1 plus another 2 divided by x plus 1. And I can integrate each of those terms for just ln's. In fact, realize even if I didn't know what a and b were, you could still integrate this. This would just, this one would just be a ln absolute value of x minus 1. If I didn't know what a was. So you can still integrate it even if you can't find a and b. And so now this is going to be equal to, though, x squared over 4, not x squared, x to the fourth over 4 plus x squared over 2, and then plus an ln, or 2 ln, absolute value of x minus 1, plus another 2 ln of x, absolute value of x plus 1. and then all plus c. And then you can combine these two things right here, and this will be equal to then x to the fourth over 4 plus x squared over 2, and then plus, you can pull that 2 out, and you get ln of, and this will be absolute value of, we'll multiply these back together, and you get x squared minus 1. And then because there's a 2 there, and then plus c, the 2 there, you can pop that back up into the exponent, and we can get our final answer here, x to the fourth over 4 plus x squared over 2, and then plus ln. I'll drop off the absolute value because I'm squaring it. So I just have it in parentheses now, the quantity squared plus c. And that's my final answer. So we need to simplify that using those laws. So let me zoom out a little bit so you can kind of see this type of problem. And so if you wind up with a rational function, so if you wind up here with a rational function like this, and the degree is bigger on top, on bottom, the first thing you have to do is remember you have to divide the polynomials. And once you divide those polynomials, then you can rewrite the leftover part here in terms of a partial fraction. And then you can just do what we did before, basically. Okay, so let's do one more type of problem. And so we're going to do this one, part B. It's the last problem we're going to do. And this one's a little tricky. And so this is one where when we do the partial fraction decomposition, we have an irreducible piece. And that irreducible piece, to actually integrate it, we're going to have to complete the square, which is a little tricky to do. So that's why we kind of saved it for the end here. But first, notice you don't have to divide polynomials. So you have a 10 on top, and you have a cubic polynomial on the bottom, and x times x squared. So it has the right form, so you should be able to rewrite it in terms of partial fractions. The question, though, is actually how do I know that this part is irreducible? Well, you can try to factor it. You'll see that you can't. But a quick way is to use that quadratic formula. So negative b plus or minus the square root of b squared minus 4ac all over 2a. And what you're really looking for is seeing if this is negative. If that's negative, what that means is that you can't factor this in terms of real numbers. So let's just see what happens here. So here's my b is 2. So I plug negative 2 here, plus or minus the square root of 2 squared minus 4. My a is 1. We usually don't write it, but it's just 1. And then my c is the number 10. So then times 10. And then all divided by 2a, so 2 times 1, which you can see now, negative 2 plus or minus the square root. What I have inside here is basically 4 minus 40, which is a negative 36 over 2. And so that's actually equal to negative 2 plus or minus 6 square root of negative 1 all over 2. And so now you can divide this all by 2, so you get negative 1 plus or minus 3i. So very clearly, it does not have real roots, which means this thing, this quadratic right here, is irreducible. Right? So it's irreducible, which just means cannot be factored, right? Cannot factored. I guess we can say not factorable if you want. I don't even know if that's a word, but you can say not factorable, right? Or cannot be factored. All right, so what does that mean now for us as terms of an integral? This is going to be equal to the integral, and we can rewrite this. So we have divided by x, so we can write a divided by x, and then plus, we write bx plus c, because this thing is irreducible, and then we write x squared plus 2x plus 10 dx. And so now our job is to figure out what a, b, and c actually are. And so to do that, we're just going to take what? We're going to take this thing and set it equal to that thing. And then we're just going to clear those denominators. So let me move back here a little bit. And so over here, what do I want to do? Oh, actually, we'll just do it right here. Normally, I would do it where I showed you it was irreducible. We'll do it right here. And so I have 10 divided by x times x squared plus 2x plus 10. And then that's equal to an a divided by x plus bx plus c over x squared plus 2x plus 10. And what I'm going to do is just clear those denominators here. So let's clear the denominators by multiplying everything by x, because that'll clear that out, and then everything by an x squared plus 2x plus 10, because that'll clear out that, and this will be cleared out by both of those. So I put this over here, and I just get back the number 10, and then it's equal to, when I multiply it here, I'm going to get an a times x squared plus 2x plus 10. The x's are going to cancel. And then plus, when you multiply it here, you're going to get a bx plus c, and then times just an x. And so now I want to figure out, what a, b, and c actually are. And so here you have a couple of ways to do this. You can plug in numbers and find a, b, and c, or we can equate those coefficients. Right? So you can equate the coefficients, which is what I normally would do in this situation. So how do you equate the coefficients? Well, it's actually not that hard. So what we're going to do is we're just going to multiply through here by the a. And so you're going to get ax squared plus 2ax plus 10a. And then we're going to multiply through by here by the x, so plus bx squared plus cx. And then we put all the x squared, x, and constants kind of together here. So let's put that all together. And so we're going to get 10 equal to, and then I have a plus b times x squared plus, and then I have my x terms here. So I get 2a plus c all times x, and then plus a 10a. And now I equate the coefficients. And so the way that works is we take the constant terms and we set them equal to each other. So we get 10 equal to 10a. And that tells me really quickly that a is equal to 1. Just divide both sides by 10. And then over here, I have an x term, 0 times x. So I put 0 equal to the x term over here. So 0 is equal to 2a plus c. Well, that gives me some really quick information. Since I know a is 1, this is going to imply 0 is equal to 2 times 1 plus c, which tells me c right away. So c is going to be equal to negative 2. I just move that 2 over to the other side. And so now that I have c, I need to figure out the last term. So now the last term, I have this a plus b on my x squared, and over here, I don't have an x squared term. So I just take 0 and set it equal to a plus b. And again, we know a is equal to 1. So this tells me 0 is equal to 1 plus b, which tells me b has to be equal to negative 1. And so now I have my a, b, and c. So what can I do? I can come over here, and I can just plug in for my a, b, and c. And so this is going to be equal to, the integral, and my a was 1, so I get 1 over x, plus my b was negative 1, and my c was negative 2. So what I'm going to do here is I'm actually going to write this. Well, I'll write it like this. So plus, and I'll have negative x minus 2 all divided by x squared plus 2x plus 10 dx. And now here, I probably would pull that negative sign out. So I'm just going to take that negative out of there. So let me get an eraser here. So I'm just going to pull that negative out. And so I'm going to write this as minus, and I'll write this as x plus 2. So I'll pull that negative sign out in front. So there's my integral. And now I can integrate this piece here. That's not a problem, right? So I can integrate that pretty quickly. It's just ln of absolute value of x. And I have minus now this integral of x plus 2 divided by x squared plus 2x plus 10 dx. Now this is going to be a little bit tricky for me to integrate. The first step I would look for, though, to integrate this is always substitution. So the idea is like, hey, here's a function, but do I see its derivative on top? So now its derivative on top, the derivative of x squared plus 2x plus 10 is a 2x plus 2. And I don't have a 2x plus 2. I have an x plus 2. But it's almost like a 2x plus 2. These I have to have the same number in front of the x, basically. So what I can do is I can kind of pull this apart. I can write that 2 as a 1 plus 1. And so I can rewrite this as ln of absolute value of x minus the integral. And I can write this as x plus 1 all divided by x squared plus 2x plus 10 dx. And now I kind of have part of it. So here's the function, and here's almost its derivative. I'm off by a little piece. And so what I can do now is I can separate these two pieces. I'm going to separate these two pieces so that I have x plus 1 over x squared plus 2x plus 10, and then plus a 1 over x squared plus 2x plus 10 dx. And I claim I can integrate this. It can just do a guess or check, or you could do a U substitution. It's kind of up to you. So I'm going to scoot this down just a little bit here. What do I have? This is going to be equal to ln of absolute value of x minus ln of absolute value of x squared plus 2x plus 10. And then if you take a derivative of this, what is it going to look like? So if you take a derivative of this, it would be 1 over x squared plus 2x plus 10, and then times a 2x plus 2. And so I'm off by a factor of 2 right here. And so what I'll do is I'll multiply that by a half or divide it by 2. And so if you have a half out here, this 2 is going to cancel with these 2's right there because when we factor them out, they have that 2 in common. And then I have left over what? Plus this integral of 1 over x squared plus 2x plus 10 dx. And so that's going to take a little bit of work now because in order to integrate this piece right here, I'm going to have to complete the square. I'm going to have to complete the square on that. And if you complete the square on that, it's like a trig substitution, but I can do it with just sort of a basic substitution because it's really going to be a tan inverse. So I kind of see what's going to happen. And so what am I going to do here? So let me scoot this down just a little bit and over a little bit. And so this is going to be equal to ln of absolute value of x minus 1/2 ln of absolute value of x squared plus 2x plus 10, and then plus the integral. And so what I'm going to do here is I'm going to complete the square on this guy. So I'm going to add half the middle term squared to it. So I'm going to add x squared plus 2x, and I'm going to add 1 because the middle term is 2. So divide by 2 is 1 and square it. I'm going to take away 1 right next to it, and I still have that plus 10 left over here. And if we did that correctly, this piece right here should be a perfect square. So it should be x plus 1 quantity squared, and then minus 1 plus 10 is a plus 9. And so I have right here 1 over x plus 1 quantity squared plus 9 dx. So if you want to make this problem even longer than it already is, you could actually do a trig substitution on this guy. But I showed you last time there is a trick to kind of speed it up to show you that this is a tan inverse. And because it is a tan inverse, I like this trick and I usually do it. And so what I can do is I can actually turn this 9 into a 1, and I can get basically what I want. So remember, the derivative tan inverse of x, what I'm kind of going for is looking for something that looks like this, 1 over 1 plus something squared, basically. And so the idea is I can turn this into that type by getting rid of that 9. And so how do you get rid of 9? We can actually just factor it out. So over here, this is equal to ln of absolute value of x minus 1/2 ln absolute value of x squared minus 2x plus 10. And then plus, I'm going to pull this 9 out. So it's going to be 1/9 the integral of 1 over, and I'll write x plus 1 quantity squared divided by 9, and then plus 1 dx. So I'll give you a minute. If you want, I can kind of put parentheses down here. But the idea is I pull that 1/9 out. Notice if you put it back in, the 9's cancel, and this becomes 9. You just get back what you had left over. But this is very similar to that type, right? So this type is very similar to that. In fact, if I do one more step, I think you'll see it. So this is going to be equal to, let me just copy everything down, ln of absolute value of x minus 1/2 ln of absolute value of x squared minus 2x plus 10, and then plus 1/9 the integral of 1 over, I'm going to write this as x plus 1, all divided by 3, and I'm squaring the entire thing here, plus 1 dx. And now this and this are very similar. They're just kind of off by a sum by plus 1 and divided by 3. So I'm going to guess now at what my answer is going to be. So it's going to be equal to ln absolute value of x minus 1/2 ln absolute value of x squared minus 2x plus 10, and then plus 1/9. And my guess would be tan inverse of x plus 1 divided by 3. And now I'll check it real fast. So what's this derivative? Well, it'd be 1/9 times 1 over 1 plus x plus 1 divided by 3 quantity squared. And then times the derivative of the inside. So what's the derivative of the inside? Well, it's just 1/3. And so notice this and this are exactly the same. This and this are exactly the same. Oh, but you're off by 1/3. So I need to change this 1/9 here to 1/3. So if that's 1/3 there, 1/3 times 1/3 is 1/9. That does it. All right, so I was just off by a little bit, and then don't forget it's plus c. And so there's my final answer. Oh, actually, I'm not quite done. I still have a little bit more left to do. But I usually tell you guys, if you get this far in this type of problem, that's a good problem. All right, but I guess I should probably put these ln's together. So let me do the one last little step here. And then, so I should put these ln's. So it's ln, you're subtracting, and you have a 1/2 here. So it's really ln absolute value of x divided by, I have the square root of x squared minus 2x plus 10, and then plus a 1/3 tan inverse of x plus 1 over 3, and then all plus c. So I should put those ln's together. And now I got my final answer. So I just realized there's a mistake that we need to correct here. So let me zoom out here so we can kind of see this whole problem. I wanted to talk about this whole problem anyways as a whole, just go over it real quick with you guys, because I know there's a lot to this problem. There's a lot of basically movements or parts if you like. So real fast, just to review, and then I'll show you the mistake. So for this integral of a rational function, right, first notice the degree on top is smaller than the degree on bottom, so you don't have to divide polynomials. You can go straight to its partial fraction decomposition. To find a, b, and c, we equate the coefficients right here, and a, b, and c just fall out. So we can come back over here and plug in for our a, b, and c, and then we can integrate that first term. And then to integrate this thing, we kind of have to pull it apart a little bit. So the idea is that I see a function, but not quite its derivative on top. So how can I get that derivative on top? And so if we split this up, basically, right here, the x plus 2 and x plus 1 plus 1, then we can basically get almost derivative on top. So here's where my mistake actually occurred. So right here, I'm taking off this whole entire thing. But then on the next line, I'm only taking off the first thing. So this plus right here should really be a minus. So coming down here, that plus should be a minus, 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 and finally, this little plus right there should really be a minus. So parenthesis, and that should be a minus right there. So minus 1/3. So minus 1/3 of tan inverse of x plus 1 over 3. Now it's good, right? The solution's good. And then just to finish this off, so once you have a function as derivative and you split this up, this guy right here, you have to complete the square. So complete the square. And once you complete the square, basically, you kind of have a choice right here. You could do a trig sub on this guy right there, or you can factor out that 9, and then you're basically doing a u substitution, or you just guess and check and show that it is that tan inverse of x plus 1 over 2. All right, so that should correct that final answer.